into disubstituted cyclohexane, okay? Now, before we do that, we have to mention a couple things because, again, when we're looking at these and we're looking at these energetics and the stability, we always want to compare chair conformations. But again, they're going to be giving you bond line structures, right? So it's your responsibility to take a bond line structure and be able to convert it to the chair conformation, okay? And so we're going to talk about, when we introduce this idea of multiple substituents, we're going to talk about how to do that, okay? Okay, so in bond line structure, we utilize our little wedge and dash to indicate three-dimensionality, right? So what does the wedge mean?
Close to you.
So it's coming out at you, right? So we have our wedge here, meaning it is coming out of the plane of the board. And what does the dash mean? So dash is going to be going away from us or going into the board, okay? Now, as we move through taking this guy and trying to convert it to the chair conformation, what we're going to define for the wedge is we're going to say that the wedge, since it's coming out at us, we're going to define it as going up, okay? So our wedge is going to be in an up position, whereas a dash, since it's going in, we're going to say that it's going to be going into a down position, okay? So if we have something on the dash, we're going to consider that going into the down position. If we have something on the wedge, we're going to consider that up, okay? So now, if we're taking this guy and we're going to convert it to our chair conformation, first thing is drawing the chair, right? So I'm going to start with my right-hand chair. Draw down, draw across, connect the dots, okay? So now, I'm also going to go through and say, all right, I'm going to call this carbon 1, I'm going to call this carbon 2, and on my right-hand chair, I'm going to call this carbon 1, and I'm going to call this guy down here carbon 2. Okay, so we have a carbon 1, and then we have carbon 2. Okay? Now, if we look at carbon 1, we have two options, right? We have an axial position, we have an equatorial position. And if we look at our actual molecule here, right, so again, this is carbon 1, who is up in this position? Is it the axial position or is it the equatorial position?
The axial.
It's the axial, all right? So again, what we mean by up is we're coming above the plane of the actual ring. So right here, for carbon 1, there are two options. We have axial, equatorial. Axial is the up position for carbon 1. So for this guy, for chlorine, we've defined it as up because it's a wedge. So we're going to put that in the axial position because at that guy, wrong one, because at that position, that is what is up, the axial position, okay? If the chlorine is up in the axial position, then what's in the equatorial position? We can go ahead and draw that on too. Just an H, right? So if we want to go ahead and add on the equatorial position here, again, this guy is going to be parallel with, this guy is going to be parallel with this guy and this guy. So then I draw this guy out, and this is going to be my H. Okay, so then that's one. We'll put on our little chlorine onto our axial position. Now as we move to carbon 2, we know that we have a methyl group that's supposed to be going down, right? So again, we have an option. We can put it in the equatorial or the axial. Who is down at carbon 2? It's axial again, right? So because this is the down position, we're going to put our methyl group, because it's going down, in that axial position. So this will be our methyl group. Okay? So then again, if we want to go ahead and draw the equatorial position on, what is the equatorial position at that carbon 2? It's hydrogen again, right? And now it's going to be parallel to this guy and this guy. So we've got a hydrogen coming out here. Okay, and so we'll go ahead and add on that methyl group onto our carbon 2 in the axial position. Okay, so this is what we've defined. Again, we're defining wedges as coming up, and we're defining dashes as going down. Yes?
Is it okay if we put the hydrogen on the other side?
No.
No, it has to be.
Because again, if we look at this, where is the hydrogen?
Oh, yeah.
It's not pointing into the ring, it's directly coming out. Okay. Same thing here, it's not going into the ring, it's directly popping out. Yes.
So if there were both wedges, then the bottom 2 carbon would be an equatorial?
So if they're both, it's not the carbon, this would be down still, right? The 2 carbon would still be down. The down position for carbon 1, though, if it was a wedge, is the equatorial position, because the up is the axial.
And what about for carbon 2?
Carbon 2, if it was a wedge still, it's still down. For carbon 2, that down position is always the axial.
Okay.
For carbon 1, that up position is always the axial. Okay.
Wait, I'm just saying that if the methyl had a wedge instead, then would it
The
be
methyl
with
does have a
H?
wedge.
What?
The methyl has a wedge.
Well, that was a dash.
Oh, pardon me, so sorry. Okay, yes, sorry. Where it's axial, equatorial. If the methyl had a wedge, then the up position of carbon 2 is not the axial because it's pointing down. The up position is the equatorial.
Also, then where the hydrogen is at.
Where the hydrogen is at, yeah. So it goes around. Again, axial helps you kind of see what's up and what's down. If you need this guy to be up, this position is down, so it has to go into the equatorial.
You kind of choose whatever is kind of the most going down. If it's going down, go with whatever's going down.
So again, if you could look around these, it's this idea of what's above the plane. At this position, this equatorial is technically above the plane. It's not as much pointing up, but it is slightly pointing up. Okay, so then that's one ring, right? So we've got our carbon 1, we've got our carbon 2, we've got up, we've got down. What's going to happen now, though? This is not the only ring conformation. Right, so now we're going to ring flip. So we've got nice little equilibrium. We've got a ring flip. And again, we're going to try to draw our left-hand ring, left-hand chair conformation. I'm going to get this guy. I'm going to get this guy, and this guy. Okay? So again, if we take our ring and we flip it, right? Now, carbon 1 is here. We've got carbon 1. We'll go ahead and highlight that. And carbon 2 has now moved to here. And we'll highlight that. So this guy is carbon 2. And we can write that 1 and 2. Okay, so we were in the axial for carbon 1. We're still up. Where is it moved to now, though?
Equatorial.
It's moved to the equatorial position, right? This is still for carbon 1 on this left-hand ring. This is still the up position because the down is the axial now, okay? So this guy has moved to the equatorial, and we can go ahead and draw that in right here. So this is our chlorine. Now, same thing as we move along to carbon 2. This is carbon 1. Where has the methyl group moved to? To the equatorial as well, right? So again, we were here. It was down. It was in that axial position when we flipped the ring. Now this guy is up. This is still down. It's just the equatorial position that's down now in this left-hand ring structure, okay? So for this guy, we'll go ahead, we'll find our parallel lines, and then we'll draw the methyl group out here. I hate blue. I think it's the light. You know, it looks really good on here, but it's just a projector, okay? Okay, so that's the big thing, and that's what I'm trying to stress here, is that up and down are not, oh, it's always axial, it's always equatorial. It depends on the position, okay? So if you draw the right-hand ring, the axial for carbon 1 is always up. The equatorial is the down, right? For carbon 2, the axial is down, the equatorial is up, okay? Okay, so now if we thought about, well, we'll come back to this because we're going to do a problem, but we're also going to be considering the energetics between the two, right? Because again, one of these is going to be favored, and we're going to talk about that once we get a little practice drawing these chair conformations. Okay, so now let's take a little time. Got a couple of disubstituted cyclohexanes. And I want you to draw the two chair conformations for both of these molecules. Right? So again, you can define whatever you want as carbon 1. That's the big thing to note. For this one, I would say this is carbon 1, 2, 3. For this one, I would say this is carbon 1, this is carbon 2, and so on. Okay? Yes?
For B, is CH just pointing this is what it is? Or
So
this
this
is an
is
attachment?
This is an ethyl group. right? But it's saying that this is an ethyl group going into the board. So this is an ethyl that's going in. Okay, so go ahead and give this a shot. For both A and B, you're going to draw 2 different conformations, depending. So you should overall get 4 different chair structures out of this. Okay, so give it a shot, push pause, and then come back, and I will draw out the answer. Okay, so I'm going to start with A. So we'll write over here A. And so in A, again, I said you guys can define the carbons however you want. I've started with this carbon being carbon 1. That's going to make the bromine carbon, carbon 3. Okay, so now we talked about in that previous slide how, okay, anything on the wedge, which is coming out at us, we're going to define as being in the up position at whatever carbon we're dealing with on our cyclohexane ring. And then anything on the dash, which is going into the board, we're going to define that as being in the down position at whatever carbon we're talking about. Okay, so for A, the first thing I'm going to draw is, again, what I've been referring to as this right-hand ring, which is the right-hand carbon being the uppermost carbon. So again, if I start with a shallow V, and I draw this guy down, and this guy, and then we'll get this guy. It's not super pretty, but we're going to go with it. I can pick whichever carbon on this ring that I want to be carbon 1, right? So that is up to me entirely. I preferentially will pick specifically this carbon because it's always there. It's always the easiest one to find, right? So if I did that, hold on, I want to finish making this a little bit prettier. Because, yeah. Okay, so if I did that, if I said this guy is going to be my carbon 1, then I usually also will move in like a clockwise direction and how I number the rest of them. So if this guy is carbon 1, then I would say that this is carbon 2. This guy specifically is carbon 2, and then this one is carbon 3. But if you had wanted to go the other way and say that this was 2, you could do that, and then this would be 3. Both of those would be correct answers, right? I just tend to go in the more clockwise direction when I number these things, okay? All right, so then starting at carbon 1, we know we have a methyl substituent, and that methyl substituent is on the wedge, so it's going to be in the up position at whatever carbon we're at. So if this guy's carbon 1, the up position is the axial position of this carbon, right? At this carbon, the axial comes up above the plane of the ring. And the equatorial, so the equatorial, which is going to be parallel to this guy, is actually going to be the down position here, okay? So if axial at this carbon is up, then we're going to go ahead and draw our up methyl. And then the other thing that's implied, which is on the down, we can go ahead and draw that here, is that hydrogen, right? So we can go ahead and draw in that hydrogen, which is in the equatorial at this position, which is down for this carbon, okay? All right, so then as we move around the ring, so if I go to carbon 2, I know that at carbon 2, the equatorial is down, right? It points down below, oh, not equatorial, the axial position is down now. It goes up, down, and now the equatorial position, which is parallel to this guy, is actually the up position. Again, at carbon 2, we're not super concerned. These are both just hydrogens. Now as I move to carbon 3, so axial went specifically up and then down. Now again, we're at an up position at carbon 3. So at carbon 3, the axial is up, and that's where we want the bromine. Bromine is also going to be up. It's on that wedge. So this guy would be here. And then in the down position here is the equatorial. Equatorial is going to be parallel to this guy, so it's going to come out like this. Now, the things that you really would have had to have drawn to actually show me this conformation, you don't have to draw any of these hydrogens, right? So this is just kind of keeping track of where we were along the ring. And you don't have to draw these hydrogens either. Again, it's just keeping track of where we are around the ring, okay? But if you wanted to draw them, you could. It's up to you. All right, so now, if that is our right-hand ring, then we're also going to go ahead and draw the left-hand ring. So this is going to undergo a ring flip because, again, we want both conformations. So then the first step in this is drawing the left hand, the other version of the ring. So again, we'll start with our shallow V. Now we'll come down from the left carbon and we'll come up. This guy's going to come down, and then this guy's going to come down. We'll connect the dots. So again, like I say, this gets really ugly when I start to draw these left-hand carbons, or left-hand rings. Okay, so again, this is where a model kit will be very helpful. If you've defined this guy as carbon 1 over on the right hand, that becomes this carbon in the left-hand ring. Okay, so that guy is carbon 1. So we can say this guy's carbon 1. Therefore, you'll follow this guy to carbon 2, and now this guy is carbon 3. Okay, so again, it doesn't matter which version of the ring you're drawing, right? The methyl in both left and right is still going to be up. The bromine in both left and right is still going to be up, right? They're still going to be on those wedges. The only thing that changes is what position is actually up at each of the carbons, right? So on the right-hand side, the axial position was up. Now that we've undergone a ring flip, it's actually going to be the equatorial position, which is up. Because now this carbon, if we draw the axial is now down. That methyl is still in the up position. So the methyl now is going to be in the equatorial position, which again is parallel to this guy. So we can draw this guy out. So this is CH3. That hydrogen is in the axial. This is in the equatorial. And again, it's hard to see this whenever we're drawing these rings on the board or on the page. But this equatorial position is up. If you actually had a model, you would see that this guy in this position is above the plane of the ring. Okay. So now, same thing as we go around. If this is carbon 2, we don't care about it. We come to carbon 3. Carbon 3, if this guy has the axial as the down, then the equatorial is going to be the up. The bromine is in the up, so we also have to draw it there. Equatorial here is not parallel to this or this, but instead it's parallel to this guy. So if I draw this guy out, we've got bromine in this position. Okay, so these are the two different conformations. Again, you don't have to include the hydrogens, but it's just helpful for me to keep track of where we're at. And in this one, we've got both of our substituents in the up position in this version of the ring, which are both in the equatorial position. Okay, so then we move on to B. So B, we've got carbon 1, carbon 2. This guy is up, but now our ethyl is going to be in the down position. So again, I'm going to go ahead and draw my right-hand ring first. Draw down, 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 down. I'm going to define this guy as carbon 1. And there's a methyl here at carbon 1. That methyl is up. And we know at this position, in this ring, up is the axial position. So I can easily draw the axial and say that this is a methyl group. Again, I like to continue numbered this way, so this is what I'm going to call carbon 2. At carbon 2, in our two-dimensional structure here, we've got an ethyl group going down. And so our carbon 2 is this guy, and specifically at this carbon, the down position is also axial, because remember, axial goes up, and then it goes down, and then it goes up as we move around. So down here is the ethyl group, also in the axial. So this was axial up. Now we have axial down. And you can represent this as just an ET if you wanted to. You could also draw out CH2, CH3 if you wanted to, or you could really just draw out the bond line version of the structure. But again, for one of these versions, both of these guys need to be in the axial position. So this is our right. This is our right. We're going to undergo a ring flip. And we're going to draw the left-hand version of our ring. We're going to attempt to draw it. Okay, yep, upset with that. So we've got this guy, this guy. This guy's going to come down. This guy's going to come across. Nope, that's not what I wanted. I want an eraser. Eraser. This guy, a little bit more, down, a little bit more, and then down. Okay, so, God, that's really ugly. I really hate drawing those. Okay, anyways, we've got our carbon 1, which becomes this guy in this version of the ring, and then we've got our carbon 2, which becomes this guy in this version of the ring. Okay, so now, at our new carbon 1, at this guy, our substituent is still going to be in the up position. The up position now is not the axial, because axial points down for this guy. The up position is instead equatorial, which points out, it's parallel to these guys, which points out. So this guy is our methyl. Then we move to carbon 2. Carbon 2, we need that ethyl group in the down position of this carbon. So this was a hydrogen. So up for this carbon is the axial position. Down is going to be the equatorial position. That's going to be parallel to this guy. So we can draw this guy as an ethyl out. So again, the second version of this is essentially, let me erase these hydrogens so I'm not confused. The other conformation here has our methyl group in the equatorial position, which is up at carbon 1. And then it has our ethyl group in the equatorial position, which is down at carbon 2. Okay, so hopefully you guys got that. Monosubstituted cyclohexane. Now we're going to talk about energetics and how to know who is the highest energy chair conformation, who is the lowest energy chair conformation with multiple substituents on it. Okay, so let's say, for example, that we had our little disubstituted cyclohexane. Yes.
You might have already mentioned this, but for ethyl groups, you don't draw 2 lines in the chair. It's always 1 with ethyl.
You can draw, if you wanted to draw this out, you could draw this and this. That's fine.
Okay.
It's preference, as long as it's correct.
Makes sense.
Yeah. Okay, so same thing. We've got a disubstituted cyclohexane. Okay, when I go in here, I'm going to go through and say, okay, this is going to be my carbon 1, this is going to be my carbon 2, this is going to be my carbon 3. Carbon 1, we have an ethyl group on the wedge, right? So we're going to define that as the up position. So this is up. Carbon 3, we've got a methyl group on the dash. So we're going to define that as the down position at that carbon. Okay, so we go ahead and we draw our right-hand chair. We're going to say that this guy is carbon 1. And at that position, on our chair conformation, who is the up position? Is it axial or is it equatorial?
Axial.
This position, carbon 1 on our first chair, on our right-hand chair, who is the up position? Is it axial or is it equatorial?
Axial.
It's axial. Okay, so we go ahead, we put our ethyl group in the axial position. We move over to carbon 2. At carbon 3, we need a methyl group that's in the down position. Okay, now, the axial position at carbon 3 is doing what? It's pointing up, right? So the axial position, which is a hydrogen, is pointing up. That tells us that if the down position has to be in the equatorial position, okay? So that means that, okay, our methyl group, since it has to go down, axial is pointing up, then it has to be in the equatorial position, okay? So we do that. We do that for our first chair. That's our first chair conformation. Now we're going to have to do a ring flip, right? So in our ring flip, we're going to draw our left-hand chair. Again, this is still carbon 1. This is carbon 2. This is carbon 3, as we've defined it. Now, at carbon 1, the axial position is down, right? So if the axial position is down, but ethyl is still up, it has to go into the equatorial position, and that's fine because we're flipping the ring anyways. And then at carbon 2, that methyl group has to be down, and now the axial is down at carbon 3. Okay, so we flip it, and we've got this guy. Okay? So now the question is, who is the lowest energy chair conformation? For monosubstituted, where did we want to put our substituent to be lowest energy?
Pointing down.
We needed to put it in the equatorial position, right? Because that was going to be anti, okay? So in the first chair conformation, do we have one of our substituents in the chair? No. My God. Do we have one of our substituents in the equatorial position?
Yes.
In the first chair conformation, yes. Yes, so number 1, we do have one of our groups in the equatorial position that ends up being the methyl group. So we have methyl equatorial. And then we have ethyl, unfortunately, where? In the axial position, okay? So then in number 2, our other version of the chair, do we have anyone in the equatorial position?
Mhm.
Yes, ethyl, right? So we have ethyl now in the equatorial, right? We have methyl, though, where? Axial. So again, we want our substituents in the equatorial position. That's going to be the lowest energy chair conformation. Unfortunately, both chair conformations has one in the axial, one in the equatorial. Who do you think is going to determine who wins this? The biggest group, right? So this goes back to the energetics, right? As that substituent got bigger, that energy difference between the two got larger, right? So when we compared the methyl to the tert-butyl had a large energy difference, meaning that it was always going to favor the putting the tert-butyl group into the equatorial position. So who's bigger, methyl or ethyl? Ethyl. Okay, so because of that, we want to put ethyl into the equatorial position. Which chair conformation does that? Number 2. Okay, so because this is bigger overall compared to the methyl group, right? We want to put it in the equatorial position for the lowest energy state. So this is going to be our lowest energy chair conformation. And so the majority of the time, if we looked at the distribution of these guys at equilibrium, we would find this molecule in this chair conformation because, again, it puts the ethyl group into the equatorial position. This one, which has the methyl in the equatorial, the ethyl in the axial, is going to be the higher energy chair conformation. Just blurs off into the higher energy chair conformation. So number 2 is going to be favored. It's going to be more stable at equilibrium. Yes.
Higher energy, less stable.
Higher energy is less stable. Low energy is more stable. We're always tending towards lowest potential energy or lowest energy state.
Okay, so favorable, lowest energy.
Lowest energy is most favorable, most stable. Okay, so with that in mind, I would also refer you back to that table that I showed you with the energy differences, because sometimes there's going to be a competition between a couple. So the last little bit that we have in class, I want you to do some of these, and then we'll go over the actual solutions. So I have 2 molecules here, and I want to know who is the lowest energy chair conformation for both of them. So this incorporates our up-down, right? It also incorporates determining who's more energetically stable, who has lowest energy. And again, we're always wanting to put the biggest group in the equatorial position. So start by drawing the chairs for both of these. Then look at them. And then try to figure out who's lowest energy. Okay, so again, I would have paused the video, try to answer these, and then watch the solutions, which I'm now going to go over. I'm going to start with A. Okay, so in A, again, I'm going to define this guy, my top carbon, as my carbon 1. And then I'm going to define this guy as carbon 2. And we're here. And so now at carbon 1, we've got a methyl group on the wedge. So this is going to be at the up position on our cyclohexane ring. And then we've got this guy, if you'll see, is a nice Y. It's a 1, 2, 3 Y. So this is an isopropyl group. And I'm going to abbreviate just isoprop. Okay, so this guy is also on the dash here. So this, whatever axial versus equatorial, the dash, this is going to be in the down position of whatever carbon it's on. All right, so now we're going to look at the two different conformations to figure out which one is the lowest energy. I'm going to draw the right hand ring first. So right hand ring, I'm going to define this guy as my carbon 1. And again, I'm going to move in this clockwise fashion. I'm going to define this guy as my carbon 2. So we have carbon 1. And then we have carbon 2, okay? All right, so carbon 1, we have a methyl group in the up position. So if we're at this carbon specifically, the up position is that axial position. So we can draw this guy as a methyl. I'm going to go ahead and abbreviate this methyl. So we have a methyl at the 1 position, which is up. And then as we move to the 2 position, our next substituent is an isopropyl group, and this is going to be in the down position. So at this carbon specifically, the down position is the axial position. So we have, I hate it when it does that. So we have down and isoprop. Okay, so on this right-hand version, we have axial as the up position, and then we also have axial as the down position. On carbon 2, we're going to have this undergo a ring flip. So now we'll draw the left-hand ring. I just don't know why that gets so bad. I think it's this one. Up, down, and then we'll just erase a little bit from this guy and connect the dots. Okay, that looks a little bit better. So make sure to connect the dots. Okay, so now, again, we had this guy as our carbon 1 over here. That's going to become this guy as our carbon 1 here. So go ahead, say this is carbon 1, this is carbon 2. And I just want to kind of draw this in a little bit better. Okay, so now if the methyl was in the axial on carbon 1 in the right hand ring, then it's going to move into the equatorial on carbon 1. That's going to be the up position now. So this guy is our methyl. It's equatorial in this conformation, and again, this is still the up position. And we'll go to carbon 2. At carbon 2, we've got an isopropyl. It's supposed to be down. So the up position here is axial, the down is equatorial. So it's going to be parallel to this guy. So it's going to come out here. And again, this thing is going to be an isopropyl group. So this is also equatorial, but now it is down. Okay, so I'm going to go ahead and erase this thing I drew here because this is only going to confuse people. So we have two versions here, right? We have both of our substituents in the axial position versus both of our substituents being the equatorial position. I'm looking for the lowest energy conformation or configuration. That is going to be this guy where both of my substituents are in the equatorial, because again, equatorial energetically is more favorable. Moving them into the axial position is going to cost energy, so this guy is going to be my lowest energy conformation, and it's going to predominate the overall makeup of my cyclohexane molecules at room temperature. Okay, so that's number one. Number two, we get a little bit more complex, and we're going to have to think about this a little bit more. So in B, we've got, we'll say, carbon 1, carbon 2, carbon 3. So we've got 1, 2, 3. At carbon 1, we have a methyl in the down position. Carbon 2, we have a chlorine in the down position. So again, we have dash, dash. And then at carbon 3, we have a chlorine in the wedge, which is up. So anytime it's on the dash, it's always going to be down. Anytime it's on the wedge, it's going to be up. Okay, so I'm going to go ahead and draw my right-hand ring first. Okay, and I'm going to do the same thing that I've done before. We're going to have 1, 2, 3. So we have 1, 2, and we have 3 over here. I'm going to start at 1. I've got a methyl group in the down position. So at carbon 1 here, the up position is axial, the down position is equatorial. So I'm going to get rid of that axial. I'm going to draw the down position, which again is going to be parallel to this guy. So this guy is a methyl group, and it's in the equatorial position. At carbon 2, we have a chlorine in the down position. The down position here is the axial position, so we can just draw this straight down. So this guy's a chlorine. And then we have at carbon 3 in the up position of chlorine, this carbon is carbon 3. The up position here is the axial as well, so we'll draw chlorine up. So we have an equatorial methyl, we have an axial chlorine, and we have another axial chlorine. We're going to undergo a ring flip here. We're going to draw the left-hand ring. Okay. God, it makes me mad. Okay, so same thing, right? We had carbon 1, 2, 3. Now it's going to be carbon 1, 2, 3. We have a methyl group at carbon 1 in the down position. At this carbon now, the down position is axial, so we can draw this down as a methyl group. So we have an axial methyl group. Now we have at the carbon 2 position, we have a down chlorine. Up here is axial, so down is equatorial. It's going to be parallel to this guy. So we have a chlorine in the equatorial position. And then at carbon 3, we had an up chlorine. So the down position here is axial, the up is equatorial. Again, it's going to be parallel to this guy. So we have an equatorial position coming out here. So then I'm going to erase these extra axials that I've drawn so we don't get confused. And I'll go ahead and fill this in with chlorine. So this is also equatorial. Okay. Now, if we're looking at these two different conformations, here we had an axial chlorine. We had an axial chlorine. We had an equatorial methyl. Here we had an equatorial chlorine, and an axial methyl. Right? So you would think, okay, well, we'll say this guy is number 1, this guy is number 2. In number 1, we had 2 things in the axial position and 1 in the equatorial. Here we had 2 things in the equatorial, only 1 in the axial, right? And so again, if we're looking for lowest energy conformation, we want things to be in the equatorial. So you would say, oh, well, you have 2 things in the equatorial, so this must be lowest energy, right? And you would say, okay, well, that's great. But you actually have to look at the numbers here, right? So on that previous slide, I had given you some numbers for having, or the energetic penalty or the energy associated with having various types of substituents in that axial position. And so here we had found that for chlorine, if you look back on that slide, that ends up being about 2 kilojoules per mole. Same thing for this chlorine. Any chlorine is 2 kilojoules per mole for putting it in the axial position. So overall, the energy penalty here is 4 kilojoules per mole. Whereas if we look at the axial methyl group, that ends up being actually 7.6 kilojoules per mole, right? So total energy penalty of putting that methyl group into the axial position is 7 kilojoules per mole, right? Versus only 4 for having 2 axial chlorines. So because of that, because this is lowest, this is the actual lowest energy conformation. Even though you have 2 things in the axial position, those 2 things don't cost as much energy as having this one guy, right? So With respect to these numbers, I don't expect you to memorize them. Please do not even attempt to memorize them. That's silly. It would either be obvious, like this one, where you literally have two things in the equatorial versus two things in the axial, or I would give you the numbers myself in some sort of exam or on the homework, and you would be able to calculate who is actually the lowest energy conformation, right? But this guy, number 1, is lowest energy, even though there are two things in the axial position, because those two things don't cost as much energy as having this one thing in the axial position does. Okay, so that is it with respect to cycloalkanes. I don't know how long this is going to go, so when I upload this, we'll see how long it takes. And then I'll maneuver my next lecture accordingly. So the next chapter, we're going to deal with stereoisomerism, and I'll introduce that whenever we get to that on Thursday. Okay, so yay, good luck. Email me if you have questions, and okay, bye.